In that case, it's a pleasure to introduce Professor Woods, Richard Woods, who is an emeritus professor here, as you know, at the University of Michigan. He received his Bachelor's of Science from Notre Dame University. And after that, he came here and did his Master's and PhD at the University of Michigan, working under the supervision of Professor Richard, who I hope you know. He taught briefly at Michigan Tech, and then shortly after joined here at the University of Michigan as an assistant professor, associate professor, and and of course a professor. He was department chair also. But kind of a miracle happened here in the 70s with Professor Woods and Professor Richard and the team in Michigan. Hopefully you know about that, but that's actually part of the presentation today. This is the place where soil dynamics was born. There was tremendous work was done. This book was written on the fundamentals of soil dynamics. And when I asked about Professor Stoike about writing a book, he said, there is nothing more to be written beyond this book. And anyone who knows soil dynamics, they just use this book. Everything else is data. And he is, of course, a pioneer in geophysics and soil dynamics. And he has received numerous recognitions, awards for papers, for contributions in the field. He's a member of the National Academy of Engineering. I think he's the only faculty member in our department who is a member of the National Academy of Engineering. I think so. Which is the highest honor an engineer can get in the country. And of course, the highest honor within the AC Geo Institute, which is the Terzaghi Lecture, which he delivered, I think, in late 90s, 99?
97.
97. And more recently, in 2012, he was recognized as a hero of the profession. There are, I think, like 6 or 7 heroes within the Geo Institute, and he's one of them. And he's also my personal hero. So he has taught lots of classes here at the University of Michigan, and most recently soil dynamics, a graduate level geotechnical testing class, and offshore geotechnics with emphasis on foundations. But because he's not teaching this semester and next semester, we thought we could at least, we all benefit by at least listening to him as part of this seminar series. So without further delay, Professor Woods, thank you very much for giving this presentation today.
Well, you're welcome. I do want to maybe correct a little bit of the information on the National Academy members. There is another living member, Robert Hansen, structural engineer. He's emeritus faculty also. But since Demetrius brought this up, the National Academy members in the College of Engineering get together for lunch every now and then. Anyway, they talk about present and past members, and one of the things that they brought up not too long ago was, how are we choosing chairs in the departments, and how many of the current chairs or the recent past chairs would be National Academy candidates. And we went around the table telling how many of their chairs had been National Academy members. And we're the only department with 3 National Academy members who have also been chair of this department.
Oh, wow.
It just, but it still gets us no recognition. The dean just looks right past civil engineering and has nothing to do with, and that's a whole nother topic, and maybe we'll talk about it someday, this building sitting out here. That shouldn't be there, but that's another, as I say, another whole topic. Well, this time you have invited a ringer here into the audience who will not let me tell any lies. Larry Yadley has been around the department almost as long as I have. He's vice president of SME and has been a great friend of the department and helped us enormously through the years, and I've participated with him in consulting over a span of 50 years. You're going to get reminiscing from me because of the topic here, but the EWRE building, before that was even thought about, Larry was doing soil tests and cutting undisturbed blocks and testing the soils along the slope where that building now resides. So anyway, I just wanted to let you know that I will speak only the truth today, since there's nobody or somebody here that can check me up on it. And I'm going to turn my telephone off here so it doesn't ring and disturb us. So the geotechnical, or probably I should have written here previously, it was soil mechanics was the topic, the title of the specialty in civil engineering that started back in 1928. There were not very many schools at that time who were studying soils as an engineering material. Of course, the Terzaghi and Casagrandis were pioneers in this area, but in terms of people doing local, what we would say geotechnical or soil mechanics work, we have one of the earliest participants was on the faculty here at Michigan. So we'll start with a discussion of okay. This is the list of faculty who were specifically assigned or designated as soil mechanics and geotechnical faculty. And William Housel, you see, spanning from 1923 to 1971. Housel got his degree in what else? Structures. Everybody starts out in structures and finds a way to maybe generate more interest or expand a little bit their horizons by moving on to geotechnical. But Bill Housel got his master's degree in structures and was hired on the faculty in structures. And the Wayne County was developing quite rapidly then with the Ford Rouge plant along the Detroit River and the Rouge River. And they needed a lot of help in terms of building highways and bridges in the Detroit area. Now the Detroit area, like about 4 or 5 other cities located on the Great Lakes, I mean Toronto and Chicago, and Cleveland, Erie, Pennsylvania, these places all were built on lacustrine post-glacial clay. So it was usually almost normally consolidated and quite soft. So Bill Housel started his career in learning about that material, and that is specifically the material that guided his research and design consulting work. So we'll talk about the developments that Housel brought along, but you see here the list. Getz was a Housel student. Richert came here from the University of Florida, and we'll talk all about that. Jack Hall came with Bill Richert. Don Gray was hired from Berkeley in mid-60s. I was hired a year later, having studied with Richard here, Professor Ritsu was hired 86, Mikulowski 99. Russell Green, who was here with us for a few years, and our current Zekos pair. This is the list as far as I know. Now, there were adjuncts, particularly former students and colleagues of Housel, who sort of taught his courses. But they were not official members of the faculty until Bob Getz. Now, I'll talk a little bit more about Bob Getz later, but Housel was responsible for developing the Michigan Department of Transportation Geotechnical and Pavements Laboratory in the basement of East Hall. Hall is what it's called now. It was East Engineering when engineering had part of its operation on main campus. East Hall is along East University Avenue, and now it's housing psychology and mathematics and things that don't really mean much, so it used to be good engineering. In the basement there, the highway department helped Housel establish a lab. And this was in the 1930s. After the Second World War, the airport called Willow Run, where Ford Motor Company built a bomber an hour during the wartime, the government gave the airport to the university, like it did all over the country. Airports were given to universities for $1 or something like that, just to transfer title. The other one that I know most about is at Texas A&M University, where we have a national geotechnical experimentation site. Housel grabbed space out at Willow Run as well. And he had, by that time, was working also in pavements, not only for automobiles, but paving airports. After Housel, we got this building. Now there was, here on North Campus, what was called Fluids 1, Building Fluids 1, and that was a portion of what is now mechanical engineering. But then there was Fluids 2, and then Fluids Annex, which is this north-south building that we're sitting in now. And this building, from its beginning, housed soil mechanics labs, because it was opened in 1974. Bill Richard came in 1964, not 70, opened in 64. Bill Richard came in early 60s, and this was one of his promised, but it was promised to him in any case when he came. In this building, we had initially soil mechanics and paving people. So asphalt and Portland cement concrete had labs in this annex, which is G.G. Brown now. And if you walk along the east-west corridor on the lowest level of G.G. Brown, you will find a plaque identifying the Housel Lab. It was named for him. He didn't ever work in it. And then finally, in this annex portion we're now just calling G.G. Brown Lab, there is the Rich Art Lab, soil dynamics lab downstairs. Now, why can't I make this thing move along? So this is a picture of Bill Housel. Was taken sort of toward the end of his life. He retired in about 74 and spent a little while in Hawaii after his retirement. I had one course with him, and it was an experience, but we won't go into that. Now, some of Housel's major contributions dealt with how do we measure strength in these soft lacustrine clays. And the principal way that he wanted to do it, or learned to do it and promoted, was the double ring shear. We'll see a picture of that in a minute. He moved on beyond that to something he called a stabilometer. Translate triaxial. But of course we know triaxial is not true triaxial because it's an axisymmetric problem and we have only two stresses to deal with, and that's what stabilometer dealt with also. We'll talk about that a little more. He developed a miniature penetrometer. The standard penetration test was around for a long time. In the 20s even, and widely used in the 30s. But he developed a miniature device that could be used principally at the base of caissons. You go down inside and measure the strength. He developed a bearing capacity theory, which is still a mystery to me, but you'll see how it looks. But he did develop a pile load test interpretation method, which is still in use by the Federal Highway Administration. They moved away from it for a long time and came back to it under Jerry DiMaggio, I think. He picked up on that. Now, the double ring shear this is a picture from a paper, so it's not very sharp, but it has some of the main characteristics here that I just want to point out. The sample is collected in a thin wall that has three segments and thin wall tube. Generally, you push or drive the sampler into the ground, and the clay comes in here. Then this portion is mounted in that kind of a bracket, and on the bottom of this center ring, there is a place for a hook and a container, and he just used lead shot. You put more and more lead shot in until it fails. And so that's the basic concept. And here is a little better, sharper drawing. This is simply the process of pushing a tube in, getting the central ring under this rigid portion. Here is the hook. And so you can watch displacement and force by adding up all of the lead shot. And here are various containers for lead shot, depending on how strong, how big the container is going to have to be to cause it to fail. Now, you'll notice that there is no stress applied in this direction, and independent of confining pressure. So it shears along two circular surfaces, and you can compute the area of those and the weight, and we get a shearing strength. He used this approach to find shearing strength for bearing capacity calculations. The next step then why are we going backwards?
Can you click here? Yeah, but we were just there.
Okay. The stabilometer, probably the best view for understanding it is the lower right-hand corner there. And of course, Housel was doing a lot of pavement work, and it looks to me like this is an asphalt specimen in there with aggregate and asphalt binder. But he used the same thing for soils. And of course, he had a rubber membrane around the sides. This was a metal cylinder. We have a version of it in the lab. You can see if you're interested. The load is applied here through a common testing machine. And the cell pressure was applied by putting loads on this piston. Piston communicated with the pore water. And so sigma 3 was applied by putting that load on. But what you'll see, what you don't see, what is most prominently missing, is a way to measure pore pressure inside the specimen. And this was one of the points that Housel never picked up on from Terzaghi and led to their lifelong arguments about the effective stress. So here you can see the plate for the pore pressure. These are windows here and here. You can see through if you want to watch this thing happening. And of course, this is a pretty robust chamber, so it was it could be used for the asphalt testing as well. Okay, now let's see if that'll move forward. All right. The Housel penetrometer, miniature penetrometer. Well, you say miniature. This is about 3 feet tall, but the penetrometer itself is here, and it looks like this is in backwards. It really doesn't matter, but then the weight is picked up here and dropped. Well, this is the version that could be taken down in a caisson, but it used the same approach in the lab to build specimens and learn how strong you could get them. And so here was a version for the lab, and I'm not even sure how to describe that element. But the next slide here, we get it? Okay. This is all of the framework. This is the actual sampler. Inside there is the sleeve, the segmented sleeve, 3 pieces to it. 1.25 inch pipe, sharpened at the end, driven with a 20-pound weight. And so it was light enough, we'll say, that you could take it to the field and one person can operate it and so forth. And I have used this device to test at the bottom of caissons, sort of what the intended purpose for designing this apparatus. So here was the simplified view. And I think the last one that I used I had to borrow from SME. I think they have the last one operational in southeast Michigan. I don't know where anybody else would use it, but in any case, I use this for testing the rock at the bottom of caissons that supported Corning Incorporated's devices for manufacturing optical fiber. Well, Housel developed a bearing capacity theory, and here you see the mechanics of it. And if you'll just blink and say, I understand, that's as far as you're ever going to get, I think. But in any case, you see the various elements, and there is shear on all of these surfaces. The S sub C, which is the cohesion that he measures from the double ring shear device. He says that he developed the theory based upon these photoelastic models. In the late 40s and 50s, and maybe earlier than that, that I don't know about, photoelasticity was an important experimental tool. And probably few of you have ever dealt with photoelasticity, but some materials are what you call birefringent, and they will refract light at different angles based upon stress. So this is a bakelite, a plastic type material model, clear, illuminated with as white a light as you could get at that time, not laser, of course. And here is a concentrated load, and the stress is developed. Well, then in an attempt to create uniform load, we see multiple points, and I think this is an interesting photo, because here we see all of the individual point loads, but when you get a certain distance away, we get right back to the same basic shape that the individual loads, is that St. Venant's principle?
The St. Venant principle.
Yeah, that distributes the load. And then Housel looked at the principal stresses and the shearing stresses, and I cannot go from this to his theory, so we're going to just bypass, and I show you again what is his basic explanation for the equations that he derived. They are not particularly widely used. However, you will find some people with Wayne County who still know about them. And so here's the load over the area, stress, and 4 different terms, and the terms take into account sort of the same sorts of things that Terzaghi does, but I'm not going to try to explain them any further. Now, Housel did not publish a lot except in engineering reports to Michigan Department of Transportation and Wayne County, and in any case, not very many widely publicized research papers. However, he did write a laboratory manual for soil testing, described how you'd use his stabilometer and his double ring shear, and even the miniature penetrometer. And he was writing applied soil mechanics. And you can, Edwards Brothers were signed up to publish it, and they published a little bit in 38, a little bit more in 55, a little bit more in 60, never more than that. And I have the last version, the 1960, because I took his course in 1964, and that was the version that we were working from. Now, Housel had some quite famous disciples. Donald Berry, probably the most well-known, a very well-known transportation professor at Northwestern University, and he retired only a few years ago. We have Donald Berry's thesis downstairs, if anybody wants to ever look at it, in which he used the stabilometer. Very interesting. Ernest Jonas was the soil mechanics leader at Tibbet, Abbott, McCarthy, Stratton, which was one of the leading consulting firms in New York City. They were the principal engineers on the Tarbela Dam in Pakistan in the mid-70s. Ragnar Ingemarsson, he was Housel's student about the same time that I started here. And Ragnar went back home, and I don't know if you would guess, oh well, the word is up there, so you know he's from Iceland. But he went back and became the, I don't know, transportation engineer for all of Iceland. Ulrich Stoll was one of Housel's students who was probably one of the most revered geotechnical or soil mechanics practitioners in southeast Michigan until his death probably 10 years ago. Dick's been gone. Only 4? Oh, I think it's longer than that. You know for sure. Okay. See, he's checking me up and being sure that I. Well, I just mentioned one of the more famous controversies between Housel and Terzaghi. In 1936, Harvard, or I guess they called it the Cambridge Geotechnical, first international conference on soil mechanics and foundation engineering. And Terzaghi was certainly the lead. And we have downstairs in our labs a very long, narrow picture of the attendees at that Harvard conference. And a lot of very famous people in there. A very young George Osterberg was very prominent in the pictures. And but Bill Housel's picture didn't appear. And when he was asked why he was not in the picture, he said he was back in his hotel room writing a discussion on Terzaghi's effective stress concept. So he didn't get in the picture. And they went on with that controversy the rest of their careers. Now, I mentioned Bob Getz. I don't have a picture of Bob. Was a master's student of Housel, and he taught undergraduate courses here, and then he moved on to be assistant dean for the undergraduate program in the College of Engineering. His brother, also an MS student with Housel, went on to teach geotechnical engineering at Purdue, Bill Getz. So it was a soil mechanics family. The next phase of geotechnical or soil mechanics and foundation engineering progress at the University of Michigan came about with the hiring of F.E. Richert Jr., Frank Edwin Richert. His father's name was also Frank Edwin. So he's Junior, but his mom didn't want to call him Junior, and they just picked Bill. So has nothing to do with any of the names in the family. He just became plain Bill. And so that's what most of us know him as. And the interesting thing is his father was a professor at University of Illinois. And if you look through the literature and just look for F.E. Richert, you're going to find papers by his dad, and you'll think, what in the world? He's talking about concrete columns. And it was senior, not junior. So Bill Richert served in the Navy in the Second World War, went back to University of Illinois and studied with Nathan Newmark after the Second World War. His thesis was on fatigue in metals. And when he got his PhD, there weren't a whole lot of jobs available, but one was at Harvard University, and it was to work with Professor Westergaard. And Westergaard, of course, was in mechanics. He wasn't soils, or he wasn't structures. He was mechanics. And Bill's dad would have had a heart attack if he hadn't taken that job to go work with famous Westergaard. So Bill took the job at Harvard, and within 6 months, Westergaard died. So he didn't have a mentor any longer. But at the same time, we're talking late 40s, early 50s. Terzaghi was teaching periodically at MIT and Illinois, and Casagrande had moved to Harvard, and somehow, and I don't have all of the background, but Terzaghi learned about Richert, and he picked up the mentorship that Westergaard had left. And so Terzaghi became Bill Richert's mentor at Harvard. And he said, you're going to study soil dynamics. And so that's what he did. And he produced 2 PhD students at Harvard who began their work by looking at a continuum. What is the consequences of applying a load to the surface of a continuum? And went on then from there. And Xie did his work at Harvard and went back to China. So let's see now. We've got Richert at Harvard. It's important to know that he took summers to work with Muser Rutledge, which was also a big consulting firm in New York. And he went there to get some practical experience. And it turned out that I think he went there 3 summers, and each summer resulted in a new technical paper in then the transactions of ASCE, and 2 of them won awards. Mainly on well, one of them was with Terzaghi on tunneling, stresses around tunnels, and the other was on the behavior of drains, the lateral consolidation associated with installing drains. Now, I don't think they were wick drains at that time, but they were vertical columns that were much more permeable. Now, some of Richart's disciples, some of you will recognize Bob B. He's a professor at Berkeley, probably about retired now, isn't he? I don't know. Anyway, that's the last I knew. He's a member of the National Academy. Lyman Heller. Now, these were students of Richart at University of Florida. The first four. Lyman Heller went on then to become the chief geotechnical engineer for the NRC. And so he was involved during the heyday of nuclear power plant construction, 75 to 85. He was the Nuclear Regulatory Commission's top dog. Bobby Hardin went from his PhD work at Florida to University of Kentucky and spent the rest of his career at the University of Kentucky. John R. Hall Jr., who we call Jack, came here with Richart. He hadn't quite finished his PhD at Florida, but almost. And so he came with Richart and submitted his thesis to Florida, got his PhD, and taught here. Similarly, John Leismer, whose name, if you were in earthquake work, is quite familiar. John Leismer was with Richart at University of Florida, and he moved up to Michigan. He had not progressed very far in his PhD work at Florida, so Leismer's degree is from Michigan. And why I don't have, oh, there I have him in here, sure. Yes, the reason is the chronology here, because there was a student working here in soils when Richart came, and he took him on, and that was Yong Shea. So Shea became Richart's first PhD student exclusively at Michigan. And then Leismer got his degree at Michigan, although he started at the University of Florida, Gainesville. Then Vince Drenovich and I joined as students of Richart at the same time. We had met each other at Notre Dame. He was doing his undergraduate work and I was doing my master's at Notre Dame. And we met there. I went from Notre Dame to the Air Force Weapons Lab in Albuquerque. Vince came directly here, got his master's at Michigan then, and then we both did our PhD. Sharif Afifi, Sharif started his career after PhD with Richart in practice at Bechtel, and then at Bechtel Houston, and then he was transferred to the Alaska pipeline, and spent several years then, or a few years, on the pipeline in Alaska, and wound up back here in Ann Arbor, where he worked for Bechtel on nuclear power plants. And I spent a couple summers working for Sharif with Bechtel during the nuclear power construction heydays. He's now a professor of international business at Madonna College in Livonia. Ken Stokey is probably the widest known of Richart's student. He was he was co-advised by Richard and a little bit by me, but you know, it turned out that Ken and I worked first on my thesis. He was my slave, and he was a master, first an undergrad and then a master's student, and so we worked together, and then I got hired on the faculty, and I became became co-director of his thesis, and we worked together trying to figure out what his thesis was going to be. And it was kind of well, I think you've got about enough. Write it up. It wasn't anything particularly special, but what we did develop at that time was the first geotechnical application of cross-hole seismic testing. And then Ken went on with that. Probably our most famous international person is Wolfgang Haupt, who is at University of Munich in Germany. Chun-Soo Chan was at one time vice president of Daewoo Construction, and I don't know what he is doing now. But and George Athanasopoulos, Professor Ada's father, was a PhD student here in the late 70s. He went directly back to Patras and has served his career at the University of Patras, and has sent us a dynamic duo here for Geotech at Michigan. Well, I spent a lot of time. Contributions by Bill Richard. A lot of marine geotechnology, which we really don't do much with here, but when he went to the University of Florida, he was doing weirs and breakwaters and all sorts of shore protection throughout Florida. And he wrote about bulkhead design using tiebacks. Richard worked with Terzaghi on stress distribution around tunnels. Well, of course, it was elastic materials, but that was the starting point, and they have a famous paper on stress distribution in the material surrounding a tunnel. And then in soil dynamics, he really got the world started on resonant column testing. Yeah, it had been done first by the Japanese in the 30s when they were trying to use cellophane as the confining membrane. Had a lot of trouble with that, but the concept was there. It was picked up by Shannon and Wilson, a consulting firm in Seattle, Washington, and the Corps of Engineers in the late 40s and early 50s. And Richard then picked up on it at the University of Florida, particularly with Hardin and Hall, and then work that continued on here. Field testing, he was quite insistent on making tests in the field, measurements of shear wave velocity in the field to compare with what was measured in the lab. And essentially is setting the foundations for cross-hole seismic and SASW and MASW, all those things that have followed on. He really got started the investigation into how do you design footings with single degree of freedom systems, and the work of John Leismer, who first did single degree of freedom systems with constant coefficients, that is, constant properties, frequency independent properties, which we also learned was not quite right because the stiffness and damping of soils is frequency dependent. So then the impedance compliance people came along and worked that process for foundation design further. And he, at the same time that Seed and Idris and the group on the West Coast were defining the strain dependency of shear modulus and shear wave velocity. He was promoting that with resonant column work here at Michigan, particularly with Drenovich's work on resonant column. He also worked on dam stability for the Corps of Engineers, along with Professor Wiley, who was on our faculty here. His book, he was certainly the inspiration for and the principal author of really the first textbook in the United States, Vibrations of Soils and Foundations, and that text persists to be a good foundation for starting into examining soil dynamics. I'll just move these quickly through the soil dynamics work. First started probably late 50s actually, but this device would be around 1960 at the University of Florida. Hardin. Here is an early device by Hall, and you see how long the specimen was. At that time it was thought it was necessary to have a long specimen, but and this happens to be one that's being driven vertically for primary wave propagation, but similar device for shear. And then to look at the importance of shearing strain amplitude, Drenovich developed the hollow specimen. So this is what the early device looked like. This is a hollow specimen, and it was the clay specimens were developed by drilling a hole through the specimen. The key then was how do you get the membrane in the center and drainage strips, and here the specimen is ready and the apparatus. The next you see cross-section view through the specimen. The whole idea was to have uniform strain in the specimen. If you have a solid specimen, you have zero strain at the center and maximum at the outside. This way, we have almost uniform strain in the wall thickness, and that was used then to develop the hyperbolic strain relationships of Hardin and Drenovich. But here you see a young Ken Stokey holding a specimen, drilling it through with a wood auger. This is K.Y. Lin, who is one of our students who went on to work in Palo Alto, California, and I think he is still there. The only thing that I have to admit for Lin was, until we let his wife play with us, he was the champion at ping pong. As soon as Chris, his wife, started, she was so much better than the rest of us. We all had to quit. Drenovich, here is the long Tor device. Long Tor resonant column, both torsional and longitudinal on the same specimen at the same time. This is the Hardin oscillator, which drives it for resonance and torsion, and a longitudinal drive mechanism for the axial. And there is Professor Drenovich, 20 years ago, I guess. Additional resonant column equipment, a high amplitude device by Hardin. Hardin did this while he came to Michigan on a summer appointment with Bill Richard in about 1961. And here, I guess, is probably the most sophisticated of the devices we have now, the Drenovich torsional shear and resonant column combined. It's showing rather old electronics, and the last time this was fired up was more than 10 years ago. But in any case, that's an important development in the resonant column devices. Bill Richard received many honors in the ASCE, Terzaghi Award, the Terzaghi Lecture, and a membership in the National Academy of Engineering. A few other members of the geotechnical community who have given the Terzaghi Award, Terzaghi Lecture, and George Osterberg, and Dapolonia, and George Sowers, and I think it's Cook, and Bramlett McClellan. All right, so then we can finish off the with some of the other faculty who have taught in the geotechnical program. Jack Hall, of course, was Bill Richard's student. He came to Michigan about the same time I did, and I took courses with Jack. Jack really was, I think, the founder of our field work. Very insistent on the practices in the field, and of course he developed resonant column devices, and he went on to be a practitioner with Dapolonia Associates, and then Stone and Webster. He's currently still teaching at Worcester Tech in Massachusetts in the Department of Civil and Mechanical Engineering. Donald Gray was the next hired, and Don Spann essentially '60s, '70s, '80s, and '90s. Some of his students, one of the early, very spelling problem up there, isn't there? Anyway, Frank was a very promising faculty member at Northwestern and died very early. He was a chain smoker and wouldn't give it up. Peter Boscher went to the University of Wisconsin. Peter died of a cancer also, but not lung cancer. Ollie Maher was department head at Rutgers University and is director of a transportation institute, which he has grown into a large and important component of their civil engineering at Rutgers. Peter Brenner spent his career at Electrowatt. No, not entirely. He also taught at Asian Institute of Technology in Bangkok and has worked at Electrowatt Engineering in Switzerland. And Suda Chen, the most recent and local engineer with the Michigan Department of Environment. Ooh, another environmental, huh? Environmental quality, and co-author of one of the texts with Don Gray. Don's contributions, the evaluation of cut slopes. At one time, I don't know how often it's going on now, but timber companies would come in and take all the timber off of a mountainside and make it very subject to landslides. Evaluation of rising damp in the UK, a lot of old buildings, masonry buildings, and the moisture would by capillarity move up through the walls and deteriorate the walls. But he's probably most famous for the last two here, biotechnical stabilization of slopes and landfill analysis and design. And he has books on these last topics. Three of his principal books here with the co-authors associated with those. And I've been here since '64 and on the faculty since '67, and retired a few years ago. Some of the people that I feel I've worked with closely, Ken Stokey principally, and Wolfgang Haupt. I worked with Haupt both here at Michigan and in Germany. I spent about a half a year at Karlsruhe University in Germany. Chung-Soo Chan and I worked on building a large quicksand tank, which has subsequently been destroyed, but we did a lot of testing on that. George Athanasopoulos and we did quite a bit of work on testing of full-scale testing of piles, and or I should say testing of full-scale piles. Dennis Hiltonen was one of my students who, along with Nenad Gukunski, who came after him, really developed on Ken Stokey's SASW work and expanded and improved upon that operation. Gukunski at Rutgers has been department head there, as well as Ali Maher. As a matter of fact, for a number of years they had only Michigan department chairs. Yang Shea became their chairman. Gukunski and Maher went there at about the same time and succeeded each other as chairs at Rutgers. So that's why they're in the Big Ten. Why else would they choose them to be in the Big Ten, except for their civil engineering geotechnical program? Nasser Al-Shaya, Kevin Hoppy is the CEO at NTH Consultants. Sharif Afifi was at NTH Consultants and now a professor of business at Madonna College. And probably most outstanding of the MS students is Larry Yadley, who has been with SME for, what, that's been 20 years now, isn't it? And with Stoll Evans Woods before that, and with Stoll Evans before that. And Larry has worked with us for a long time. I'm running a little late here, so you can look at those without my making any comment. And some books that I've been involved with. Our current faculty, these persons are, well, Roman and Radoslav are not just beginning, but they're still writing their legacies, and just some guesses for the future. Some of the things that might be in the future for our current faculty. And this isn't the end. I hope that Michigan Group will continue to contribute to geotechnical engineering. That's all.